In this video, we're going to be talking about rooted trees. But before you go on, I strongly suggest that you look at the in-class activities, the activity for rooted trees, to introduce you to the idea of finding rooted trees within a given tree. Well, hopefully you're back from that by now. And so we're going to look at the concept of a rooted tree in this video. We're first going to discuss what a rooted tree looks like to give us a visual of where rooted trees come from. And then we're going to determine which trees can be rooted trees. And then we're going to determine which vertices within a rooted tree can be the root of a rooted tree. And then finally give a formal definition of rooted trees. So here is the visual of what we think of when someone says rooted tree, something that looks like this. So you can see that it's a tree. It doesn't have any cycles, of course. But it's sort of organized in a way that the vertex at the top, which we call the root, and then the vertices are kind of organized into levels. So we have that vertex at the top, we have 3 vertices, and the next level down. Below that, the next level down from that, we have 4 vertices, and then in the next level down, we have 1 vertex at the bottom. We can think of those as generations if we're thinking about like a family tree type of situation. Each vertex is said to be the parent of an adjacent vertex that is below it, and each vertex is said to be the child of an adjacent vertex above it, but of course the root at the top cannot be the child of anyone. So a natural question is, out of all the trees in the world, which trees can possibly be rooted trees? So and also within those rooted trees, which vertices are allowed to be the roots? So if I give you a random tree like this one, it looks like maybe, whoops, I'll go back there, that maybe E in the middle there should be the root, and it looks perfectly fine, right? So if we take E to be the top vertex, we can organize the rest of the vertices into generations. It looks like a rooted tree just fine. And again, it's the same graph that we had before. It's isomorphic. The only difference is that I've made it look a little bit different by arranging the vertices and edges in a slightly different way. But of course, if you wanted to, we could make I the root, right? So I could do something like this. Again, the same graph. It looks a little bit weird. I only has 1 child. G only has 1 child. E has 2 children. F has a child, and B has 3 children. But you can still organize it into generations, and it looks just like the same types of visual that we had before. So the lesson that we learn here is that any tree can be a rooted tree. Any vertex within that tree can be a root of a rooted tree. And so all we really mean with a rooted tree is it's just a regular old tree, but we've focused in on one vertex that's going to be our root that we identify as a distinguished vertex. That's the vertex that is the root. So a rooted tree, as a formal definition, is a tree along with a distinguished vertex V of that tree T. And of course, that distinguished vertex V is called the root of the tree. So now that we know what a rooted tree is, I encourage you to go ahead and finish up the activities on rooted trees in the PDF file with this video.